Hello everyone, welcome to lecture 34 of the course Diffusion in Solids. So this week, the previous three lectures we have seen how the CalFAD approach works, and then some implementation softwares that are used to use the CalFAD approach to make thermodynamic phase prediction and kinetic simulations and so on. And in the last lecture we also talked about the databases, how they form a very critical part of these computational tools. So today actually what I am going to show you is some ways to solve a couple of problems using the diffusion module in the thermocalc that is known as DICTRA. So although today's presentation or today's video is not a live one, we have tried to put several screenshots for you to explain the steps that you can use to perform this simulation. So I definitely suggest all of you to download this thermocalc, the educational free version, and both these problems can be worked out in this free version. So this will give you a hands-on experience of how the diffusion simulation works. So a couple of examples we will be taking today, that is a moving phase boundary in iron carbon system, and then multiphase carburization of an alloy. What is a moving phase boundary? As the name almost defines it, a moving phase boundary in diffusion refers to a boundary or interface between the two phases in a system that changes position over time due to the diffusion driven mass transport. So usually this movement is driven by the chemical potential across the boundary. And as we have seen in the diffusion couples, the interface between the two phases can migrate as the atoms diffuse, leading to the growth of one phase at the expense of the other. This some of these we saw already when we were talking about phase formation in the interdiffusion zone. So this is the schematic. Earlier we have seen that at T0 you have this two different end members coming into contact which have different concentration, and over the time you have the situation where the diffusion happens and the interface starts moving. So you can see here also it is illustrated at T0 there was this one interface. At T1 as the phase forms, these interfaces develop, and T2 they grow further. So the example that we are taking, this simulation, it models the growth of ferrite into austenite in an initially homogeneous iron 0.15 mass percent carbon alloy at the isothermal condition. So as I have said, this example only uses two elements, so it can be run in a free database package included with the software. So the alloy is steel which is having 0.15% carbon by mass, and the objective of the simulation is to see the growth of the ferrite phase into the austenite phase in this particular alloy. So what are the key parameters here for us? They are both the FCC and BCC phases are assumed to be initially homogeneous, and the transformation temperature, so the simulation is conducted at a constant temperature of 1050 Kelvin. The initial thickness of the austenite phase is 2 mm, and a very thin layer of ferrite BCC measuring 1 nanometer is present at the beginning of the simulation. So at 1050 now we will see whether this layer, how it grows into the austenite. So this thin layer, why it is drawn or why it is considered, it represents the nucleation phase of the ferrite formation in the FCC phase. So then you know, already we showed in the previous video. So this is the diffusion module that you should select once you open the thermocalc software. And so here all the nodes will appear in the project pane. You can first define the system. So you can see here the system definer. And here then you can select your desired package. Since we are talking about iron, carbon and steel, so we click the demo steels and iron alloys, FE demo, MFE demo, both it includes. So that it will also load both the thermodynamic as well as the mobility databases. So you can see here these are the two databases which are selected. Then moving ahead, we select the elements iron and carbon. So this is a binary, or you can say a plain carbon steel. So we don't need to select other elements, only an iron carbon will be enough. And usually when we are performing the diffusion simulation, we need not set the material composition, because compositions in the diffusion module vary with the distance. Then you click on the next. So please remember, again here it is I am showing you the screenshots, but please do take some time to perform this simulation hands-on by downloading the software. After which then you can go to the diffusion calculator. Here you can see and perform the step 2, which is selecting this particular tool. And here you can define the geometry. So you can select the composition, which is in mass percent by default, and then change the length unit to the micrometer. So that is because the order of the penetration depths are typically in this range in the metallic solids. Then keep the default geometry, which is planar. Then all diffusion simulations require at least one region to be defined. In a case our simulation, we are talking about the ferrite and austenite. So these are the two regions here. So we can click this plus sign here. You see this region. So we can click the plus sign here to add a second region. And let us name the region 1 as ferrite. And you can basically define the width. Let's say it is 0.001 micron, which is the initial layer thickness, 1 nanometer, and the number of points to be 10, and default linear type variation. Then in the linear, as the name suggests, the grid type is equidistant. So you will have the equidistant dots. You can also see the dots here. So these are the equidistant dots that are represented. Then this is known as the domain. Now you can further add. So before adding another, we also need to know what phase is this. Okay. So this we are selecting BCC A2 phase, but in this system you may be aware that okay, this is BCC phase which is to be considered here. But let's say if you are not having an idea, then how do you know this phase? So for that, what you can do is you want to basically right click on the system, define a node, and say create new successor, and go to the equilibrium calculator. So at the temperature of your concentration and the composition, you can see what are the phases that are at equilibrium. So in the configuration window, you can select the phase diagram under calculation type. So you can see a window here. So you can see this option phase diagram, and you can select that. Then you right click on the equilibrium calculator, and then again create a new successor and go to the plot renderer. Then afterwards you can click on the renderer and then select perform now. So this kind of a phase diagram you will see appearing in the results pane. Since our composition interest is very close to this axis, so you can zoom it a little bit, and that will show you this zoomed phase diagram, and you can clearly see it is BCC A2 plus FCC A1 at this composition, which is 0.15. So basically then you can also add the label at 1050 Kelvin and 0.15% carbon. So this is the label 1050 and 0.15% carbon. which corresponds to our conditions. Then you can further click on the show details. So why is this step needed? You can see the mass fraction of the carbon here. So this carbon content is about 10 power minus 4 mass fraction carbon, which is equal to 0.01 mass percent carbon. So this is the value now we will use in the diffusion simulations. So basically you return to the diffusion calculator and set the phase to BCC-A2. This is what we saw just now. Then click edit next to the composition profiles here, and you will see this kind of a window or a dialog box opening. Then we select Fe as the dependent component and keep the carbon profile as linear from 0.01 mass percent left to 0.01% right. So this is what we saw in our equilibrium calculation just now. Then you click apply. Then let us do the same steps for the another region, which is the austenite region. So here you can keep the width at 2000 micron and the number of points as 50. See, remember why we are keeping the width larger here, because it is we are simulating ferrite growth into the austenite. That's why ferrite was considered as a very thin layer which represents the nucleated phase, and austenite is a much larger region. Select the number of points to be 50 and change the type to geometric. So we want more points closer to the interface, so you can change the geometric ratio to 1.05. So which means that the spacing increases by a factor of 1.05 from the left side for each grid point. So you can see here, this is the number of points that are represented in the austenite region. So this here, the lines that you see, they represent the ferrite region. We already saw that it was only 1 nanometer. So again, this is very small against the width of the austenite. So now here in the region 2, set the phase to FCC-A1, which was the other phase we saw on the phase diagram. So we saw the region BCC plus FCC. And then again composition profile, you click edit. So you will see this kind of window opening, and keep this kind of setting. So here dependent component is iron, carbon linear profile, then from 0.15 to 0.15. So then you click apply, and then this is the compositions we have defined. So remember, now we have to define the temperature. So we take isothermal condition here, and then we select the temperature to 1050 Kelvin and the simulation time to 30 hours. Then click next. Then after that select the plot renderer one node. Now you will see this kind of dialog box where you can set the axis variables. So here change the axis variable to time, and time, the unit is in hours, and y-axis variable is the position of the interface. Okay, so how much is the interface moving? This is basically what we want to see, and the units is micrometers. Then you click on perform. So you will see that this kind of a plot appears on the result pane. So you can see this is the position of the interface, and this is the time in hours. So after 30 hours, the interface would have moved by this much distance. Now this shows, as I said, the position of interface as a function of time, and this is a typical, you can see a typical parabola shape which is characteristic of many diffusion related phenomena. If you want to see how it will look like at a longer annealing times, then go to 300 hours, select 300 hours and click continue. So see here that at 30 hours actually it did not reach a saturation. So it was still moving. So that's why now we try to see what happens at 300 hours. So now at 300 hours, you can see that this line becomes saturated. So the interface, the position has now become constant, and it is no longer moving. So that is to say that now the BCC has reached equilibrium with FCC. You see two different colors here. This is blue, this is red, which represents the continuation from our previous simulation, that was for 30 hours. Now, if you want to add a second plot, then right click on the diffusion calculator 1, then put create new successor plot renderer and rename the node composition profile C. So here the limits are from 0 to 2000 and the steps to 200. So here now you can see on the y-axis you can put composition of carbon in the mass percentage region. So basically this we are trying to see how the carbon composition varies. So here set it 0, 1 e power minus 4 to 300. So this will plot the simulation for all these 3 of the times. So basically what we are trying to see here is that at different times, if you remember the first slide that I showed you, the schematic at different times. So like that we are trying to perform at 3 different times, 0, 1 e to power minus 4 and then 300 in hours. So then you click on perform. So you see that this is how the profile looks like. At time t equal to 0, this is like this, and at time 300 hours, which is represented by the green color line, you can see almost an equilibrium is reached. And this is the situation at just beginning after the time t equal to 0, basically it is 36 hours. So now let us move on to the, so that was the first example, which is the moving phase boundary problem. Now we move to the next example, which is a multi-phase diffusion simulation. So here what the intention is to explore the multi-phase diffusion simulation, and the example is carburization of a nickel chromium alloy. So multi-phase means so far when we talked about the diffusion, we always consider diffusion through one phase. But let's say you have steels where two phases are together stable, then how the diffusion proceeds, can I draw the profile in that? This is how we can simulate here. So we are taking the example of a nickel chromium alloy. So here it is modeled as a multi-phase region with the M7C3 and M3C2 carbides in FCC matrix using an activity condition for the carbon at the left boundary. And again this diffusion module can be run in demo mode with up to 3 elements. So that should not be a problem. Select as usual the diffusion module. Then first we need to define the system. So now here you can still click steels and Fe alloys database package, because it has the data for nickel and chromium as well, and it will load both mobility and the thermodynamic database. So now here you have to select nickel, chromium and carbon, and you specify here the compositions here are shown. Then you go to the diffusion calculator. So here you accept the default for the composition and the geometry section. So the geometry is the planar, composition is in mass percent. And then we define the region like we did before. So the first region is the austenite. Here the phases are FCC M3C2 and M7C3, and we can set the width to be 0.003 meters and 100 points, and the ratio we can put 1.02 and put it as a geometric variation. So you can see again here that the points are initially closely spaced and then they become more far apart. So this after this selection, then you can see that there are multiple methods to estimate the overall diffusivity in a material with multiple phases. Because if there are multiple phases, which diffusivity value that we need to take. So, generally what we use is a homogenization function, which is basically a method to combine the diffusivities of individual phases into an overall one value. And to get the accurate results, we must choose a homogenization function that matches the material's microstructure. So, here go to the options. You in this tab you will see the options. Then you will see that the homogenization function what we can use, and if you click here, you can click the general upper Hushin-Strickman bound. So, basically this function assumes the phases are arranged as concentric spherical shells. So, the multiple phases are arranged as concentric spherical shells, and this provides the upper bound for the effective diffusivity. After specifying that, return to the conditions tab and then click edit the composition profiles. Then dependent composition is selected as Ni here, and both the chromium and carbon are linear. You can set the chromium from 25 to 25 and carbon from 1 into e power minus 4 to 1 into e power minus 4. Then click apply. Now, the left and right boundary conditions in the diffusion module, it allows us to fix the activity or composition for each of the boundary. So, basically what you do is, in the left boundary condition, you select mixed zero flux and activity for the for this. So, chromium has zero flux. Chromium is not allowed to enter or leave the system. So, we want to set a carbon activity boundary condition where the activity should be given with graphite as reference. So, we will set carbon activity to 1. So, here we click type 1 rather. So, the reference states for the components, they are defined in the system definer on the components tab. Here in the components tab, these reference states are defined. So, you can select the component, and here you can basically uncheck the box to next to carbon and set the reference state to graphite. So, here the reference state can be selected as graphite. Then again go to the diffusion module. Now, it is the time to set the temperature. So, let us say we want to do this at 1123 Kelvin, and let us say select the time to 1000 hours. Then go to the plot renderer one, and under the x-axis you can uncheck the box next to automatic scaling. Instead you set the limits from 0 to 0.002 at a stepping of 5 e power minus 4. Then click on perform. So, this is the result that you will see, first result of the multiphase diffusion simulation. So, this is the mass percent carbon, and this is the distance, and you can see that there is a jump in the concentration profile. So, there is a drop, and that indicates the presence of a phase boundary or an interface between the two phases. Beyond this interface, the carbon concentration exits a smooth gradient implying diffusion within a different phase or matrix. So, you can see here, here it is a smooth gradient, here it is a smooth gradient, but here there is a sudden jump. If you want to set up an additional plot, then phase fraction of all phases as a function of distance should be given. So, what you can do is go to the advanced mode, which allows users to put additional combination of axes. In y-axis, you can select the phase fraction in the axis variable, and here again uncheck the automatic scaling box and set the limits from 0 to 0.4 at every 0.05 interval. Then click on perform. So, you will see this kind of a plot which is basically phase fraction of all the phases against the distance. So, you can see that M3C2 carbide forms closer to the surface where carbon is high, and M7C3 forms where in the material the carbon content is lower. So, this clearly tells you that there will be two phases and how they get developed. So, basically in the scope of DICTRA, the diffusion module, it proves very effective to simulate diffusion controlled phase transformation with high accuracy. Then DICTRA's development always focuses on linking the fundamental models with critically assessed thermodynamic and kinetic databases, ensuring that the diffusion simulations they represent as reliable, as realistic conditions possible for the practical alloys. To do all this, as we also highlighted in the previous video, a good quality database is necessary. And you can also try some of the other examples where DICTRA can be used, homogenization of a binary iron nickel alloy, evolution of Fe-CrNi diffusion couple, diffusion through a tube wall, micro segregation during solidification, and gamma alpha gamma diffusion couple of Fe-Ni-Cr alloys. Here are the references from which some of the information used in these slides and the data presented has been taken. So, with this, thank you for listening, and we will continue with the tutorial lecture in the next video. Thank you.